This is Unit 3, video number 1, light. When we talk about light being a wave, it has a frequency and a wavelength. The frequency is how often a point on the wave passes by some point you're looking at. So it's the number of peaks, we usually say, that passes a point per unit time. Typically that unit is seconds. So we call those hertz when it's done in seconds. You've heard of megahertz and gigahertz. Wavelength is the distance between two light points on a wave. So if I have a wave here, like this, then the distance from here to here, exact same point, is going to be the wavelength. We're going to use the Greek letter lambda to represent the wavelength. We'll use the Greek letter nu to represent the frequency. So the frequency is how many times it passes a point. The wavelength is the distance between two similar places on the wave. Obviously the light has energy as well. We all know that blue light has more energy than, say, red light. Okay? So let's do a little calculation. Our equations, E equals h nu, h being Planck's constant. Okay, it is a constant. 6.626 times 10 to the minus 34 joules seconds, the smallest unit of light or energy we're going to manipulate. Nu lambda equals c. Wavelength and frequency are inversely proportional. When the frequency is high, the wavelength is very short. When the wavelength is very long, the frequency is very low. Okay? So nu lambda equals the speed of light. Speed of light being 3 times 10 to the 8 meters per second. So let's calculate the energy of a 620 nanometer light wave. Okay, so we're going to calculate the energy. We're given the wavelength. Now the wavelength is in nanometers because most visible light, UV, infrared are measured in nanometers. So 620 nanometers, we need to have similar units between the two. We can't have nanometers and meters in the same equation. So we're going to convert 620 nanometers. Now, 620 nanometers, nano, Greek word for 9. So we've got every meter is 1 times 10 to the 9 nanometers. Well, this is basically 6.2 times 10 to the second. So 9 minus 2 is 7. So that's going to be 6.20 times 10 to the minus 7 meters. Now we can do our calculation. We want to calculate the energy. Our equation doesn't give us the relationship between energy and wavelength. It gives us the relationship between frequency and wavelength. So we're first going to calculate the frequency. Then we'll take the frequency and plug it in and calculate the energy. Okay? So the wavelength is going to be equal to, divide both sides by the frequency, the speed of light, 3.00 times 10 to the 8 meters per second, divided by our wavelength, 6.20 times 10 to the minus 7. 6.20 times 10 to the minus 7 meters. Punch that in our calculator. We're going to get 4.84 times 10 to the 14 reciprocal seconds. Or we would just say hertz. That's the unit that reciprocal seconds is named for. Now we have the frequency. And you know, I messed up here, I wrote wavelength. This is the frequency. All right, so now we have the frequency and we can calculate the energy because the energy is equal to Planck's constant times the frequency. So we can say, okay, E is equal to Planck's constant times the frequency. That's going to give us, write the wrong one in, 6.626 times 10 to the minus 34 joule seconds times 4.84 times 10 to the 14 reciprocal seconds. Okay, our seconds are going to cancel because this one's in the denominator, this one's in the numerator. punch this into our calculator, we're going to get an energy as a result of that. So we multiply these two together and we'll have the resulting energy.